I just thought it was kind of strange. Being unreligious myself. Okay, so the first chapter here should be all of it pretty familiar to you. And I've just been making pencil notes in the margins, so I'll use the textbook to remind myself of what's going on. So notation. Notation is always a problem when you're writing on the board because people write vectors in different ways. So I'll write vectors like this with an arrow over the top, and depending on the mood, sometimes write tensors with a double-headed arrow. But you will see different notations, and that can really screw things up if you don't understand them. Usually people, so this defines the velocity vector, and define the velocity is, the momentum is mv, a three-dimensional vector. Later on we'll be dealing with four-dimensional terms when we get to relativity, where the fourth dimension is time. And the usual notation, f is equal to dp dt is equal to p dot, and these are all vectors. And so that's usually taken as the definition of force. And so I would like to make a little excursion into the discussion of force here, not to get too tangled up in fundamentals. You can spend all of your time, if you take quantum mechanics, worrying about where does quantum mechanics come from, setting it up as a mathematical structure, and what are the assumptions that you need to make it work. And the same thing is true in mechanics. This matter of force, I just counsel you to put in the back of your head, is a very ill-defined concept. And there are those theoreticians who would like to say that we should do away with talking about force at all, because it's such a slippery issue. What do we mean by the force on an object? Everybody has a good sense of intuitive understanding that I apply the force to this, and that has some sort of meaning. But we talk about it in terms of the force that's applied to a point particle, and we start out by considering point particles. And then we build up structures out of point particles, either clusters of particles which are moving as a cloud, or particles like this, a rigid body where the particles are all nailed together in some complicated way, and so that one force applied to that is applied to all of point particles in there. And then as we get deeper into the subject, we find out that, of course, that there are atoms, and with a lot of electrons and a cloud around them, and the nucleus inside, which is protons and neutrons, and the protons and neutrons have quarks, and there are gluons flying around in there, and that the deeper we look, the more we find structure, and the more we find wave-like behavior of matter. But yet this fiction of things as billiard balls, which you can apply forces to as in shooting pool on the pool table, is a very useful one and has wide application. And I think everybody here understands by now that when you get to quantum mechanics, people first time around are always baffled by the wave-particle duality bet. And my answer to that to the students is always look, no one ever promised you that you would have some decent intuitive understanding of things on this scale that's so vastly away from by 12 orders of magnitude from our everyday scale. Why do you think that you should be able to describe things at that scale in a way that makes any sense to us at this scale? And the answer is, it's a kind of a miracle that we do have ways to think about these that we can interpret in terms of things that we know well, like waves and like billiard balls and so on. But quantum mechanics is what it is. It describes very, very well the way things go on very small scales, and in fact, no one has found any violation of quantum mechanics in any way, despite pushing around the limits of it very hard. So these things are useful concepts, but some of them are more fundamental concepts than other concepts, and the concept of force is one of the ones that's useful, we all understand, but I'm simply pointing out at this point in time, and then we'll forget about it, is that it's a little bit slippery, and many people would like to. People have even suggested rewriting the fundamental text so that we would never write this. We would only write things like this. And there is sometimes some application to this. For example, in engineering, if you're trying to solve a bridge truss, you know, something that's a really over-constrained system where you got things maybe going like this, try writing down the force equations for all of that, and you'll find that it's over-constrained, and you can't figure out what are the forces in any of these particular struts. You can't, because there's simply too many. There'll be too many things that you have to solve for compared to the equations that you have. And so the way that engineers in general solve these kinds of things is they make virtual perturbations to the system, and so push on the system. And with these finite element programs, you can perturb the system and look at the energy change in the system after some perturbation, and then deduce the behavior of the structure. So the question of the peculiarity of force is not entirely an academic one, but we won't further have much to do with that. I just put it as a little bee in your bonnets to worry a little bit about. And it's in that spirit that you should take all of these things and think about, do I really understand what this is all about? Okay, so we come then to F equals ma, which everybody knows since you were knee-high to a grasshopper. And so mx, for example, double dot, the second time derivative. So has anybody amongst you ever thought much about that equation? Does it seem as though it must surely be right? Does it have to be this way? Is this the only universe that we could have had?
Well, Aristotle thought it was different, right?
Yeah.
He thought it was more like F equals mv.
Yeah, but he was wrong.
That's true.
Well, mass isn't changing, so we're assuming that if force is defined as the change in momentum.
Right, that's for sure. The mass, this is assuming the mass is unchanging, first of all. But maybe I should have written as well, maybe I should have written plus m prime x triple dot plus m double prime x 4 dots. What about those terms? Why aren't they there?
First order approximation.
Hmm?
a first order approximation.
It's more than a first order approximation.
So definitely.
Well, it turns out that there's nothing in this world that prevents some of these other terms, except that we simply don't see them. And there are people that have said, this is called a jerk, by the way. If any of you jerks pose this, and you might set up an experiment to measure F equal MA, and I'm sure if you Google it up, you'll find where people have set some very strong limits on whether F equal MA is all there is. And it turns out, as far as we can tell, that's all there is. Now, once again, life gets complicated when you start getting down to more and more details. When you get to field theory, then there can be some higher order terms in field theory. So it's not quite a closed issue. For mechanics as we know it, we are stuck. That's all the terms we've got.
Field theory, is it more because you're dealing with energies and fields, and that's why people don't like to talk about forces, because everything's in terms of your Lagrangian density?
Yeah. Yeah. When I go to talk to my friend Sandeep and I try to explain something to him, I can't just draw him a little picture. He says, show me your Lagrangian. Okay, so that's an example of the kind of thing that we accept without very much question. So right away on the second page, the reference frame in which the first law, Newton's first law is valid, is called an inertial or Galilean system. F is equal to P, is equal to P dot. And in quantum mechanics, you'll find that there's a reason why we want to write things in terms of momentum more, because when we get to relativity, momentum is the nicer thing to play with. Not MV, because V becomes complicated because of dilation effects and all that, but the one that you can stick with is P dot. So then the book goes through the usual discussions of conservation theorems. So this theme will come back in time and again, as you were already seeing in if you're taking quantum mechanics and E&M in parallel, and in your senior undergraduate courses. The idea that there are conservation theorems is vitally important to modern physics, and much of what we know from elementary particle physics has to do with finding systems in which there are conserved quantities which have to do with symmetries in the system. And for instance, that translational symmetry turns into the conservation of linear momentum. And rotational symmetry turns into conservation of angular momentum.
Noether's theorem.
And Noether's, thank you. Noether's, I never know how to pronounce her name.
Yeah.
Amy Noether. Noether?
Yeah, it's like,
I don't know what the proper German pronunciation is.
can you help us, Natalie?
How is it spelled?
N-O umlaut T-H-E-R.
O umlaut?
Yeah.
O Ö? Nör?
Noether.
Noether.
Amy Noether. She was a physicist.
Is it a TH after the Ö?
Yeah, it's like,
Yeah, Newtown.
neuter.
She, as with most women, was not recognized very much in her time at that period, and when there were negligible amount of women in the field, and when they got into the field, were not allowed to become professors and things like that. But she is remembered for having been the first person to really realize the relationship between symmetries and conserved quantities and so on. So you will see references to Noether's theorem. So by the way, just thinking about the gender issues, there were, in the 20s and 30s, there were something like 5% women in physics. Guess what percentage it is now on senior faculty? It's about 5%.
Is that just here or everywhere?
Oh, here it was 0% until just recently. But fortunately, things I think are suddenly starting to change. There's more women. The studies have shown over the years that in physics we lose women around 6th grade when girls start to say physics is yucky. That's something that boys do, and it's downhill from there. But in recent years, things have taken a bit of a turn for the better, with more prominent women coming along in physics and more role models. Role models is where it's at. But it's very strange. In Italy, there are many more women physicists than there are in the US. It's very culturally dependent, I think in Germany too. But if you look at
There are
the...
not that many girls. Like in engineering, we had like a 50-50 thing. It depended on what kind. Like material science was like 50-50. And then when you go like to mechanical engineering or electrical engineering, there are barely girls. Physics too.
Right. Anyway, I do believe it's changing and for the better. We now have 2 women in the physics department here, which gets us up to 2 out of 15, which is good numbers. At any rate, yeah, good to see it changing. Okay, mechanics of a system. What did I write here? Oh, okay, yeah. There's the talk about forces being equal, Newton's law about forces opposite and equal forces, and of course that depends on the type of force that's involved. And our gravity is a nice force that's along the line of the geometry connecting the two, the geodesic, but that is not the case for